So let's say that we have a voltage source that is 15 angle 30 degrees volts. We have some impedance ZA. I'll tell you what that is in a moment. We have some current source. Let's call this 2 angle 10 degrees amps. We have some impedance ZB, and we have some impedance ZC, like so. And let's say that ZA is 8 plus J 4 ohms. ZB is 6 minus J 2 ohms. And ZC is 12 angle 45 degrees. Oh. So I have a mixed bag of impedances. Some of them are expressed in rectangular form, others are expressed in polar form. And let's say, for the sake of argument here, that we are trying to determine this phasor voltage V sub C. Okay, so the voltage drop over impedance C. Excuse me. So the first method that we're going to employ to solve this problem, just because I want to demonstrate it to you, would be superposition. All right. So since we have exactly 2 sources, we're going to wind up working this problem twice. Once with the voltage source on and the current source off, again with the current source on and the voltage source off, and then just add the results together, because that's what superposition allows us to do. So with our voltage source on and our current source off, what this guy would look like would be 15 angles here. Here's the A. Here's the B. Here's the C. Our current source being turned off in the frequency domain still looks like an open circuit. So this is what we're trying to solve for. And I should call this VC prime. We're using superposition. So how can we solve for VC prime, not E? You could, but I'm lazy. So voltage division. This is a voltage source with 3 impedances in series. We can find the result using voltage division without ever bothering to figure out what the current is. So that takes the 2-step method that you suggested and converts it into a 1-step method, right? So we could say that VC prime is 15 angle 30 degrees volts multiplied by 12 angle 45 degrees ohms divided by 8 plus J4 plus 6 minus J2 plus 12 angle 45 degrees ohms. And let me take a moment to throw this in my calculator. I get 7.255 with an angle of 49.999. So let's just call that 50 degrees. Anybody else get something similar? All right. That portion of the working out the problem in this particular way. All right, let's move along and say that VS is off and the current source is on. So to turn our voltage source off, we short it out. So we're just going to have ZA over here. Here is our 2 angle 10 degrees current source. Here's ZB. Here's ZC. And this is VC double prime. We're trying to find. How can we solve this? So we can do, I'm going to put in air quotes here, nodal analysis, but I would argue that it's not terribly efficient. And so let me explain what I mean very specifically by that, okay? We would have a node here. Let's just call this nodal voltage VA for the sake of argument, and a node here, nodal voltage VB for the sake of argument, with this bottom node, crap, chosen to be our reference. And obviously, that nodal voltage VB would be the exact same thing as that VC double prime we're trying to find. The problem that we would face is that we would have to set up a system with 2 equations and 2 unknowns, and our calculator literally can't do that with complex numbers. So that's why I would argue nodal analysis is probably not the best choice here. Okay, so if a computer were available, you could absolutely do nodal analysis. But if a computer were available, we probably wouldn't be having to do superposition to begin with. So let's try something else. Anybody else have any thoughts? I have. Okay, so we can do current, and then as a second step, we can apply Ohm's law to find the voltage drop over that particular impedance, okay? That one I feel is pretty obvious. It takes 2 steps to get to the answer. Anybody have any other thoughts? So you'd still wind up with 2 equations, 2 unknowns, right? So if you set a mesh current on the left and around that left-hand loop, a mesh current on the right-hand loop, then you're obviously going to have mesh currents I1 and I2. You'll have a KVL equation around the outside, and you'll also have that current relationship. So it's going to be a 2 equation, 2 unknown system, just like we were if we were doing nodal. Well, a different system, obviously, but we'd be in the same conundrum as if we were doing nodal, in as much as we couldn't solve it with our calculators. So we'd have to go do like Kramer's rule by hand or a bunch of messy substitution, which I've only seen 1 student in 4 years manage to do a substitution-based method and get the complex number problems right. So I would say, don't waste your time. Just too much bookkeeping. Any other thoughts? So right now, we've leaned on current division, And then with a second step of Ohm's law. Anybody else have any other thoughts? Yes, sir. A source transformation, okay? A source transformation. So on the left-hand side, we have a current source in parallel with an impedance. So we could source transform it and we'd effectively have the exact same thing that we solved in the first step. A simple voltage division would get us the answer that we're looking for, right? So that would be two steps. We would do a source transformation and then we would apply voltage division. Or we could, as was suggested, apply current division and then use Ohm's law. So the two different ways that are the most obvious are those two. They both involve the same number of steps. So I'm going to choose to do the current division method and then Ohm's law because we haven't done that yet. We just did a voltage division, but that way of thinking is absolutely perfect. Okay, nothing remotely wrong with it. So as a quick reminder on current division, I'm going to call this current here IC double prime. And to determine IC double prime, we will take our known current of 2 angle 10 degrees amperes, and we will be multiplying it by a ratio where in the numerator, we want the total impedance of the branch we're trying to find the current through. So for that case, that would be 1 divided by ZB plus ZC. So that's going to look like 12 angle 45 degrees ohms. And then in the denominator, we're going to have the reciprocal of all of the parallel branches. So that'll be 1 over ZA, or 1 over 8 plus J4, plus 1 over that numerator again. Close this guy out. Let's see what we get for this. It should be 45 degrees and then also a unit of ohms because this particular impedance is a polar form complex number. So if I did my math correctly, you should get 0.721 with an angle of 11.565 degrees. Anybody else get that? Obviously, if we had done source transformation and then voltage division, we would have gotten the exact same result. How many of you, we're not going to do it, but how many of you remember how to do a source transformation? What would we do? Okay, so the current source in parallel with an impedance is electrically equivalent to a voltage source in series with an impedance. Absolutely correct, okay? How would we get the value of the voltage source? Right, Ohm's law, just multiply the current and the resistance together to get the voltage. Would the value of ZA change when we did our source transformation? No, it's got to stay the same. Okay, trying to make sure that you guys remember these things. All right, so from here, VC double prime is just IC double prime times ZC. Which I get to be 8.652 angle 56.565. Yeah, sorry. I was concerned about the digits of the angle being the same, but that makes sense because I'm just multiplying, or I'm adding 45 degrees to the angle from the previous step, which is why those decimal points are going to stay the same. Volts, and if you'll humor me for a moment, we would then know that VC, the quantity that we're actually looking for, is just VC prime plus VC double prime, which would be 15.882 with an angle of 53.571 degrees volts. So what did you feel about that method of superposition? This problem, except for the numbers, is literally a test problem that I've asked before. What do you feel about the difficulty of this question? Let's start there too. Anything seem wild or crazy? I don't particularly think so. No, this problem was a test problem. I don't know if it will be. Probably won't be exactly like this, but something similar. I have to give you problems that you can solve using these methods like voltage division, current division, superposition, source transformations, and all that kind of good stuff. Because your calculator can't solve the system of equations. All right, so I'm going to copy this original problem, and then we're going to work it a different way. Right? Because some of you may not be fans of superposition. So let's talk about other ways that we could solve this guy. Anybody have any thoughts? Superposition is now off the table.
Source transformation with the voltage source and combine the new current source with the original.
Absolutely. So method number 2. Source transformation. So the suggestion here is that since we have a practical voltage source on the left-hand side, we could convert that to a practical current source, which would then put both of our current sources in parallel, allowing us to combine them together. And then we've made the level of complexity of the problem go way, way down because it just becomes effectively a single loop circuit. No, a single node pair circuit, excuse me. How did oh, let me erase all this crap. That's why it didn't show up the first time. It put it down towards the bottom for some reason. So our first step here is going to be to convert our current source, our practical voltage source into a practical current source. So that's going to give us some current that we'll find out in a moment in parallel with ZA. And then that bit will be in parallel with the right-hand side of the circuit, which contains the 2 angle 10 degrees amp source, ZB, and ZC like so. And I'm going to be lazy and just say that this is going to be 15 angle 30 degrees volts divided by ZA. Because because that's the exact value that it'll have. I could then observe, hopefully you all observe it as well. Those two current sources are in parallel and they are oriented in the same direction, which means I could replace it with a single current source having a value. Let me move this over so I have enough space to write this. (15 angle 30 degrees volts divided by ZA plus 2 angle 10 degrees amps. So that's the total current being provided by this composite source. Correct. And then here I would have ZA, ZB, and ZC. The ultimate goal here would be to find VC as it was before. How could I do that? We could do another source transformation here to get a single loop circuit with which we can apply voltage division. We could do current division and Ohm's law like we have done previously. Both of those are fair game. Those would be the two methods that jump out at me the most. All right, so which one do you guys care to pursue? Pardon, Justin? Yeah. So let's do since I'm calling this a source transformation, source transformation method, let's do another source transformation. All right. So we would obviously multiply that whole current by ZA. So we're going to wind up having a voltage source here that is 15 angle 30 degrees volts plus, I'm going to have to move this over. Two angle 10 degrees amps multiplied by ZA. Everybody okay with that? Understand why I did it? So I'm taking that whole current that I have on the left-hand side there and multiplying it by ZA, which is going to give me a voltage. And then I will have ZA in series with ZB in series with ZC. And just for the sake of argument, I'm going to call this thing on the left-hand side VS. And we can see then that VC is just VS multiplied by ZC over ZA plus ZB plus ZC. And now let's plug those values into our calculator, right? So 15 angle 30 plus 2 angle 10 by A X times C over A plus B plus C. 15.882 angle 53.571. Which exactly matched our previous result. Yes. No, it's being multiplied by the whole thing, right? Because I have to multiply it by the whole current that's being supplied by that composite current source, right? So when I multiply 15 angle 30 over ZA by ZA, that's where just the 15 comes from. But I also have to distribute that ZA and multiply the current as well. So the 2 angle 10 degrees portion of the current. So yeah, I'm not just multiplying that one part. It happens to fall out that way that it looks like it, but I'm actually distributing that that ZA multiplied by the whole thing. Any questions regarding this method? All right. Let's do a method that's probably less intuitive, but very powerful. No, I converted, I don't know where my page went. The practical voltage source on the left containing the 15 angle 30 degrees voltage source in series with ZA into a practical current source. So I converted this practical voltage source into this practical current source. Yes, then I added the two currents together because they were in parallel and went on my merry way doing circuit analysis techniques. All right, let's further beat this problem to death. But I'm going to use a Thevenin equivalent circuit to solve for VC. Okay. So we're trying to find the Thevenin equivalent with respect to that impedance ZC. Let me write down method 3. Circuit. All right. So since I'm trying to find the Thevenin equivalent with respect to ZC, what do I need to do to impedance ZC first? I have to take it out so that I can find the open circuit voltage seen by that, right? So that means that I would have this guy right here, 15 angle 30 degrees volts, ZA. Two angle 10 degrees amps, ZB. Open circuit terminal here. My open circuit terminal here. And this is my phasor Thevenin voltage. How can we find this? Well, yeah, but how? So, okay, so let's write that down. This voltage VB must be 0. Everybody understand why? Exactly right. There's no current flowing through the impedance, so there can be no voltage drop over it. So that leads us to an interesting revelation here. All of the current being supplied by that 2 angle 10 amp source, which I'll draw in blue, has to flow through that impedance ZA. So I would argue that we could find our Thevenin equivalent voltage here just using a simple Kirchhoff's voltage law loop because we know how much current is flowing through the different parts, right? So if I say that this voltage is VA with this particular polarity. Actually, let's do it the opposite polarity. That'll make it even easier. We can see practically by inspection that VTH is just VA plus 15 angle 30 degrees volts, where VA is nothing more than 2 angle 10 degrees amps times ZA. Anybody have any problems with this circuit analysis? Were you scratching or raising your hand? Neither, apparently. Okay. Anybody, everybody catching what I'm throwing here? Okay. It's probably may seem like an odd way to solve the circuit, but it's going to make it pretty simple. All right. So we throw that into our calculator. I get 32.835 with an angle of 33.571. Two angle 10 times ZA. Yeah. So now that I know the Thevenin voltage, I need to know the Thevenin impedance. Thevenin impedance I would find by turning off my independent sources. So that means my 15 angle 30 degrees voltage source becomes a short circuit. My 2 angle 10 degrees current source becomes an open circuit. I'm looking in, and Z Thevenin is going to be what? ZA plus ZB. Which, as a rectangular form complex number, is going to look like 14 plus J2 ohms. And so now I can say that I have this network, VTH, in series with ZTH in series. And I just want to know the voltage drop over VC. How do I do it? Voltage division, right? So that's going to look like VTH times ZC over ZTH plus ZC. X times C over Y plus C. Not getting the answer that I would expect. So I wonder what I screwed up. Saving in my calculator. $32.835 with an angle of 33.571 times V over ZTH, which is 14 plus 2I plus, there we go. 15.882 angle 53.571 degrees. Exact same result as the other methods, just a different way of doing it, right? If we did a Norton equivalent circuit technique, we're not going to here. What would effectively happen, or one easy way to analyze it, would be, since we're going to have that short circuit on the right-hand side, if we did a source transformation on that practical voltage source and combine those two sources together, we would know our Norton current in 2 steps, because that's all the current that's going to flow through the short circuit. And then we would find the Thevenin equivalent impedance in the same way, and we'd be there practically just as fast. So Norton equivalent circuit would also work here, but I'm not going to bother doing it because it's so similar to what we wound up doing with the source transformation method. You guys over the head with here. Is nodal analysis in air quotes, okay? So I don't even remember what number this is. All right. All right. So I'm going to call this voltage VA with this guy right here as my ground. If I apply Kirchhoff's current law at node A, and I'm going to do something a little bit sneaky here, okay? And if I apply Kirchhoff's current law at VA, I could say that I would have VA minus 15 angle 30 degrees volts divided by my impedance ZA plus VA sorry, that's not right, minus 2 angle 10 degrees. I don't know where my head's at. Amps plus VA divided by ZB plus ZC is equal to 0. So effectively what I'm doing here to get away with having to set up a system of 2 equations and 2 unknowns is combining those 2 impedances that are in series into a single impedance, which allows me to calculate what that voltage VA will be in a single step. Well, I say in a single step, I'm going to have to do some algebraic manipulation and crap like that, but at least I have a relationship in 1 step, right? So then I could say from this, let's say VA over ZA plus VA over ZB plus ZC is equal to 15 angle 30 degrees volts divided by ZA plus 2 angle 10 degrees amps. Everybody. Then I can say that VA is just multiplied by 1 over ZA plus 1 over ZB plus ZC is equal to that same thing, 15 angle 30 degrees volts divided by ZA plus 2 angle 10 degrees amps. And finally then, VA would be (15 angle 30 degrees volts) divided by ZA plus 2 angle 10 degrees amps multiplied by ZA in parallel ZB plus ZC. That last term may not be as obvious to you guys, but when I divide both sides by 1 over ZA plus, or excuse me, so it would be 1 over ZA, I divide both sides by 1 over ZA plus 1 over ZB plus ZC. That is exactly the what I would get for the parallel combination of ZA in parallel with ZB plus ZC. Now that I know VA, I can use voltage division to get VC. Okay. So let's take a moment to figure out what this is mathematically. So I have what I have is X, and then multiplied by A times B plus C over A plus B plus C. (21.004 angle 32 volts. And then, assuming I didn't screw that up, VC is simply VA times ZC over ZB plus ZC. (15.882 angle 53.571 degrees). Extraordinarily familiar, right? Volts. So in about 45 minutes, we calculated our way through 4 different ways to solve this problem and mentioned a couple of other different ways, okay? So I hope that that is enough proof that since we have literally beat this problem every different way we could think of, that all of your DC circuit analysis techniques, because we used damn near every one of them at some point here, are fair game in analyzing any of these circuits, okay? Nodal and mesh can be used on your homeworks and all that kind of good stuff because you obviously have computers that you can work on them with. But I would try for the smaller circuits to practice coming up with ways to work them by hand. And obviously when I give you the old exams to work from, which if somebody will send me an email, I'll do that tonight to remind me to do it. I'll post your old exams. All of those problems are obviously intended to be worked just using your good old $20 calculator. So those will be good practice for you to figure things out. Ian, what's up?
Are we going to be encountering AC circuits with dependent forces on the set?
I don't know because I haven't made the exam. I want to say probably not. It's the exact same circuit analysis that you've been doing, so it doesn't really change anything. It's just a little bit more bookkeeping. I don't think I put a problem involving a dependent source on the steady state sinusoidal stuff very often. I'd have to go back through and look at my old tests, but I can't recall having ever done it, but I don't want to say I won't do it. But I probably won't do it. Because I have Justin. So that was me. If I combine those two impedances together into a single impedance, that lets me eliminate that variable. So instead of having a two equation, two unknown system, I combine those impedances together so that my only unknown quantity was ZA. Then once I know ZA, I break those guys back out into two series connected impedances, which allowed me to perform voltage division. Okay. So I told you I was being sneaky. But it's a fairly straightforward sneakiness. Any other questions? Do you guys want to look at this circuit anymore? Do you want to do something else, or do you want to get to the lab? Lab. All right.